All right, so welcome to this EYU session on standing up for science. So I will start by showing you how science and technology are really important to the US economy. And then we'll have some faculty tell us how national funding plays a critical role on everything that we do, science, technology, and our economy. So let me see if I can figure this out. I might. So again, my name is Miguel Garcia-Garibay. I'm the Dean of the Division of Physical Sciences, a professor in the Department of Chemistry and Biochemistry. And like I said, today I'm going to try to persuade you that science and technology are the most impactful national investment. So I'm going to start by just highlighting how science and technology have made our lives significantly better. As you know, today you can get your entire genome in a few hours. That makes it possible to develop preventive medicine and to develop medical treatments that are especially for you, that only take care of your specific needs. Advances in technology have made it possible for us to communicate with each other, to draw information, to use artificial intelligence in ways that have never been possible before. We have seen self-driving cars, drones, and we have rovers roaming in the surface of Mars. Just a few years ago, that seemed like science fiction. We can get solar energy and trap it and use it well. And if you think about it, most of these technologies started in research laboratories at universities. But perhaps more importantly, humans are curious, and we want to continue trying to understand our universe. We want to study from black holes and galaxies to the secrets of biology, to the subatomic particles, dark matter, and dark energy that make our universe. And let me assure you that this is where the new technologies are going to come from. So we need to continue exploring. Science and technology are everywhere. Every aspect of our economy includes it. And like I said, almost all major breakthroughs started at a basic research university, in a basic lab, and in a basic research at a university lab. So this is really important. Now let me try to convince you that science and technology are critical to our economy. What you see here is that by 2024, the US economy, in terms of the gross domestic product, was $29.2 trillion. Now, not a lot of people know, but science and technology generate 69% of our economy. That's $20.1 trillion. Our investment in STEM research is $196 billion, which is only 0.6% of our economy. So you can see these proportions in this bar. Now you might say, what about other countries? Well, we can see that while we spend 0.67% of our economy, China, Germany, and South Korea invest 4.1, 2.7, and up to 5% of their economies. So their investment is significantly higher. To continue things in perspective, you will notice that in the top left region, we can see that investment at UCLA reaches a value of about $1.5 billion. That is combined federal, state, and foundation funding plus philanthropy. So the question is, that's a lot of money. Where does the money go, right? Well, some of it at universities like UCLA goes to pay for facilities and administration, which is often referred to as F&A costs or overhead. But the vast majority enables the research and supports the faculty and students who create new knowledge, the inventors, the technology leaders, and the preparation of high-tech professionals. And this is the part that is not quite widely appreciated. So to understand that, we need to take a look at the cost of preparing science and engineering professionals at research universities like UCLA And who pays for it? Let us start with a college degree. 4-year college we will estimate about $160,000. And that is paid for by families, loans, financial aid, with contributions from the state and federal government. A PhD, we will estimate $325,000. That's for 5 years. And a 3-year postdoc was going to be about $330,000. So these are the costs that support the people that are being trained in science and technology. But what is always forgotten is that the infrastructure that we need is significant. We need equipment to maintain the labs. We need supplies. We need instruments. And you see all of that in these figures here. So when we add all of that up year by year, we'll find that every science and engineering professional at universities like UCLA requires an investment of the order of $1.5 million. And those are your taxes. That is the national investment. So these scientists and engineering professionals create new knowledge and drive our economy. So where do they go? To answer that question, we want to follow, let's follow just a few tech companies. We've selected a few that you can see here. So how many scientists and engineers are hired by these companies? Tens of thousands. And I told you that each and every one of them requires a national investment of the order of $1 to $1.5 million. So that means that we are, as a nation, are investing $50 billion for Apple to be successful. That is the national investment. So effectively, these companies are the stewards of our investment. Now, is this investment worth it? Well, we can look at this is just their net annual income, right? So if we were to look at the gross income, the numbers will be about twice as large. But that means that the 6 companies that I have on the screen combined, their net income equals the total investment that we as a country put on research. Do we benefit from that investment? Well, the answer is yes. Technology improves our life, right? That's what I tried to tell you at the beginning. We are healthier and live longer. And actually, we have a chance to share profits. So as we know, most workers in the US actually invest in things like the 401k plan and others so that we partake of that investment. Now, it's very interesting that if you follow the stock market from 1900 to 2020 roughly, this is a logarithmic scale. So this is a factor of 10 every time. And if you look at the growth from 1900 to 1950, the growth was 2.5 times, from 80 to 200. Now, from 1950 to 2020, the growth was 50 times, from 200 to 10,000. And today, the Dow Jones is about 40,000, somewhere here. So what you see here is that there is something interesting. There is a significant change in the slope here. So what happened in 1950? President Truman created the National Science Foundation to promote progress of science, to advance the national health, prosperity, and welfare, and secure the national defense. So clearly, this is quite important. So my message today is that our national investment, your investment, enables scientific discovery through our faculty. And I illustrated here with a number of Nobel laureates from UCLA, including 2025 Nobel Prize winner in chemistry, Omar Yaghi, who was a professor at UCLA. Your investment allows science and technology to improve through our alumni, and these are some of our alumni, including the 2025 Nobel Prize winner for physiology and medicine, Prem Ramsdal. Your investment makes it possible for our faculty and students to explore our planets and the universe, and there are some examples of that here. And your investment enables entrepreneurship at UCLA, and we have some examples of the different things that UCLA has produced, among many, many others. And let's not forget the economic impact on our graduates. So the US Labor Department has indicated that there is a median lifetime earning increase of about 1.1 million per Bachelor of Science and Bachelor of Arts degree, and about 4 million per PhD degree. When you look at the numbers at UCLA, and by the way, these are just the numbers of the college, so we need to add the School of Engineering and others. This translates into about 5.54 billion of lifetime earning increases for our graduating class. So I think you will agree with me that universities like UCLA give an amazing return to our investment. So, and it takes a national investment to support research and to have the technology and the science that we do have today. And we thank all of the funding agencies that make that possible. But more importantly, we want to recognize and thank each and every one of you, because it is through your taxes and your contributions that our country is doing as well as it is. And we hope that that will continue. I will end there, and then I will next pass the microphone to Professor Amy Mainzer from the Department of Earth, Planetary, and Space Sciences. Amy, welcome.
Thank you so much, Miguel. It is a really great pleasure to be here, just because in addition to being able to be a professor here, I'm also an alum. I did get my PhD here in 2003 in the Department of Astronomy and Astrophysics. So I can tell you just how important this place is from my own personal experience. But let me talk a little bit about my own research and the importance of federal funding to the kind of work that I am able to do. So let's give it a go. So I think we'll talk about what I'm working on at the moment, which is looking for asteroids and comets that can get close to the Earth in an effort to try to predict when the next major asteroid or comet impact could be. And you would think, well, maybe this is a solved problem. I mean, we have telescopes that can explore the most distant parts of the universe. Don't we know where all the asteroids are? And it turns out we actually don't, which was quite surprising to me when I started working on this. But it turns out if we were to look out into space and imagine that we're sort of floating over the solar system, if you will, and that yellow dot in the center is our sun, and the blue circle is the orbit of our Earth, every little green dot out there represents an asteroid that we think is in the population that can get close to our planet. Now, we haven't found where most of these are yet. These are mostly unknown, and the flashing little white lights there is a telescope that we're building right now that we hope will give us a much better picture of what is actually out there. But basically, you know, the solar system is a really busy place, and even though we think we know where most of the things are, we actually don't know. So we have a lot of work to do. And hopefully in the next few years, we'll learn a whole lot more about the propensity for asteroids and comets to actually make it to Earth and cause appreciable damage here on the ground. So let me tell you a little more about how we're going to do this and the important role that federal funding and UCLA play in this process. So how might we prevent such a thing from happening? We know that asteroids and comets can impact on very long time scales, but you know, we really care about what happens in, let's say, our century. From the point of view of people living on Earth, we'd really like to know if there is anything headed our way. And so to that end, we've assembled a really good cast of partners who you can see down there representing many of the companies that Miguel referred to. And of course, the Jet Propulsion Laboratory in Pasadena is a big player in managing this new space telescope that we're building. As we like to call it, the Jet Propulsion Lab is sometimes referred to among our group as UCLA East, because so many of our grads go there to JPL. So from my perspective, and as a colleague of mine likes to say, the most important thing we can do to prevent an asteroid and comet impact is just simply find them early. Because if we can spot an object well before it has a chance of making its way here, we might be able to do something about it. But if we don't know it's there, there's nothing we can do. So to that end, from my perspective, the thing we want to do is increase our capability to see further away. We want to be able to see more and see faster. So to that end, we're building a brand new space telescope that will launch in a couple of years. It's called the Near-Earth Object Surveyor mission, and it's a mission that NASA is funding. And it will launch in about 2 years. We're a little less than 2 years from launch now. So we have a lot of work to do at the moment. But it has one single purpose, and that is to find and track and characterize the asteroids and comets that can approach the Earth most closely. So I'll just show you here a little diagram of it. This is an asteroid hunting machine that we are building. It has one purpose, and it is really to go track down the things that can get close to the planet. It's a pretty tall observatory. This is a sort of a little schematic of it up here, but basically it's got a sunshade that shields the telescope that's down here on the inside from the sun. and it's powered by the sun with lots of solar panels. We have a propulsion system that will allow us to achieve our orbit and stay pointed at the things we want to look at. And eventually, the camera will take images once we're on orbit, and we will get them back to the ground so that we have a real-time movie, essentially, of what the asteroids and comets are doing, so we can keep track of them. In any event, this thing is really being built right now. So you saw the diagram. There's some of the hardware sitting at the Jet Propulsion Lab. This is a relatively recent picture of it. So at less than 2 years from launch, we're really in the thick of building this right now. So it's a very exciting time. But the thing is, something like this is really only possible through the scope and scale of funds that are available, resources that are available through federal agencies like NASA. In other words, it's just such a big telescope. You can see how large it is. It's physically pretty big, and not only that, it uses the latest in technology that we can possibly make for the cameras. The camera chips on board this telescope are heat sensitive. They will sense the very faint heat from the asteroids as they're warmed up by the sun. And because of this, we really need some very, very high technology to be able to do this. And these sensors are actually built right here in Southern California, up in Camarillo, not too far from here. So in other words, from NASA, we get not just the funding, but we also get a really experienced workforce of scientists and engineers who know how to use and build this technology and make it work. And it takes decades to train a scientist and an engineer, like myself, like Miguel was saying, that it really is a long-term investment to help us get where we need to go. And this is not something that private industry would necessarily undertake by itself, because this is looking for asteroids and comets, as I like to put it, is we're sort of like the weather agency, except for asteroids. We're a public good. And we're there to really just make sure that we know what we need to know about what's headed our way or not. We're going to make all of the data freely available through a public website, as we've done in the past with our other NASA projects. But again, that's the power of federal funding for you. So anyway, another important thing that these projects do for us is at a top research university like UCLA, this is what gives our students the training that they need to be able to go forth and create the companies of the future and the technologies of the future. So I've got a picture here from my colleague, Professor Angelopoulos in my department, who's got a bunch of students working with him on another space mission. And we're really lucky. UCLA is top-notch in all of these areas. And so we're very happy to have the Near-Earth Object Surveyor project here. Just a few numbers. Like I said, it really takes a huge workforce of very skilled people to be able to build the best asteroid hunting telescope, hopefully, that we'll ever build. But basically, right now, just in Southern California alone, this one project is employing about 150 full-time equivalents between UCLA, Caltech, and the Jet Propulsion Lab. So we really do rely on a high-tech workforce, and we train people too. We train our students. So we have a number of grad students on the project and undergrads as well who support this project to make sure that it's going to do what we need it to do. But the point is, our students learn as they go, and hopefully our students will go off and help create the next generation of space mission that will solve other problems. So to that end, as my colleague likes to say, each dollar that gets invested in NASA science, just NASA science, this one agency, this one part of this one agency, typically returns $2 to $3 in investment in value to the rest of the world. And California, by the way, is a powerhouse for NASA and National Science Foundation. Just in 2023 alone, California received about nearly $7 billion in investment from NASA Science through competitively won grants. And that just speaks to, from NASA Science and NSF, just speaks to how well-trained our workforce is and the sustained investment that not just the federal government, but also our state has made in training professionals. And so with that, I'll hand it off to my colleague here, Dr. Thomas. He is going to come up and talk to us about exactly how we go about training some of our really accomplished students. So thanks very much.
Hi. Thank you, Amy. I think I want to just hold this in my hand. Okay, I also brought my helper, Emil. Yes, and that's me. I'm Thomas. Hi, everyone. That's me. I'm a lecturer in the Statistics and Data Science department. I've actually taught in this lecture hall before, so it feels like coming home. And so my job is to be a teacher. I'm a teacher here, and I see it as my job to train the Amy's and Dean Miguel's and Suzanne's, and maybe even the Terry Tao's of tomorrow. Oh, and something went wrong. I clicked on a wrong button, I think. Can you help me, Danny? Thank you, Danny, and we're back. Okay, so today I'll be talking about Alistair. And Alistair is basically ChatGPT, but I've made it the best possible version of ChatGPT. So to the 18 and younger crowd, I assume your teachers have told you that you're not allowed to use ChatGPT for class. You're not supposed to use ChatGPT for class. Well, I think that we should embrace new technology and move forward with it. And we should embrace the technology and make it the best possible we can. So I do allow my students to use ChatGPT in my classes, generally. And I thought once I allowed them to use ChatGPT, it might as well be the best possible ChatGPT that's possible. And so I took ChatGPT and I trained it on my own lecture materials, on my lecture slides, my syllabus, all of my materials that I provide to my students, and also materials that I don't provide to my students. And then I gave it some specific instructions on how it should interact with my students and gave it to them as a tool, as a resource, right? This is just a tool that should, make your growth and your learning faster and better. All right. So why are we doing this now, and why are we doing this right here? So our job is to teach the researchers and also the workforce of tomorrow. And I feel that in the statistics and data science department, this is one of our really important jobs, is this service, this teaching, this outreach. And statistics, in my mind, is the engine room of science. So we are the ones who drive forward the development in other fields with our methods. This project here, Alistair, was designed for my Stats 10 class. Stats 10 is taught in here, so that's our Intro to Stats class. Right now, as we speak, 768 students are enrolled in Stats 10. It's a lot of people. And in the last year alone, we had 2,222 students complete this course. Every UCLA undergraduate has to take an Intro to Stats class to graduate here. So this is important. And this is, everybody has to do this and learn about this, because the importance of data science is growing exponentially in industry, but also research. Everybody has to work with data. And so our department is noticing that. We are the fastest growing department in UCLA. If you are looking for a major, we offer two excellent ones, the statistics and data science major and the data theory major. And our graduates are doing really well. Like in numbers, our graduates make about $74K a year after they graduate in comparison to the UC average or median of $54K. So this is valuable. Show of hands, who has used ChatGPT before? This is not a test, you can be honest. Okay, that's about what I expected. So there's change. The world is changing. Education has to change too. We have to stay ahead and we have to stay on top. So the questions that I would like to answer today around my project is, number one, how does ChatGPT actually work? What is ChatGPT? Second one, what are custom GPTs? Because that's what Alistair is. It's a custom GPT that I created. And how can we use them? So first one, what is ChatGPT? I like to think of it as autocomplete on steroids, because that's really all there is to it. It does, more technically, next word prediction. Okay, so now I'm going to my helper, Emil. Can you hold the microphone? Okay, so what does next word prediction do? So next word prediction, we have a conversation, right? When you chat with ChatGPT, you get text. So you put the text into ChatGPT, and then it will predict one word, only one single word, the single most likely word that should come next in this conversation. And now it's part of the conversation, right? So now we have everything up to the conversation, including that word, and now ChatGPT will predict the one next word that's most likely to come. Based on that, right, based on everything, we predict the one most next likely word. And we keep doing that over and over and over again, one word at a time. So ChatGPT, thank you, builds a conversation one word at a time until the next most likely word is end of response, at which point it's done and it's your turn again. And so from this, there's just a statistical model underlying this. It's a neural network that does this next word prediction. And there's two main things that I would like to put focus on that derive directly from this next word prediction. The first one is that ChatGPT doesn't know anything. ChatGPT has no access to truth. It has no access to any knowledge at all. All it does is you dump a bunch of training data in it, and that means whatever people write online, that's all what it's trained on. It's written on text online. It's trained on text online. So it's super vulnerable to whatever people write online. And it will just repeat whatever people write online. That's all it does. It finds statistical patterns in online text. So it's super vulnerable to whatever's in the training data. And the second part, which is also a direct consequence of this next word prediction, is that it's super easy to lead it. Right? If you ask it a leading question, it'll fall for it every single time. Because it just builds on your question, and it wants to tell you what you want to hear. Right? The way you phrase your question, it wants to tell you what you want to hear. So it's super gullible, and it's super easy to lead it down into deep, dark places. And also, it has whatever your ideas of the world are, that's the way you phrase your questions, that's what it will tell you. So it reinforces your own thinking. All right, now we need to move to the next slide. Perfect. So then what are custom GPTs like Alistair? So custom GPTs are base GPT, ChatGPT, just ChatGPT as we all know it out of the box. And then we add some knowledge to it. For me, class materials, lecture slides, the syllabus, plus specific instructions. How should you talk to my students? In particular, we need a goal, why are you here? It needs to know what it knows, if that makes sense. You need to tell about the lecture slides and how it should interact with the lecture slides and the students. And then at the end, personalization. Alistair likes to use emojis because I like emojis. All right, so let's see how it works. So Intro to Stats is one of those classes where students have to learn how to program. And if you've ever learned how to program, that's painful. That's a hard, arduous journey. And what will happen is, here, let's look at the left. You forget a close quotation mark. And the error message you get says, unexpected symbol. Is there an unexpected symbol here? No, you're just a dummy. You forgot to close your quotation marks. But that's not what the error message tells you. Whereas if you were to ask Alistair, it tells you, hey, you forgot to close your quotations. Here's the corrected code with the closed quotations. Right, that's a much better answer. That's actually useful. Or if you ask base ChatGPT, what should I review for the midterm? Well, it doesn't know who you are. And, okay, that's okay. I had a really good GIF of a confused dog, which was ChatGPT. I was really confused. There was a dog with its tongue sticking out, but that's okay. Anyways, ChatGPT has no idea what's on your midterm because how would it, right? How would ChatGPT know what's on my midterm? But Alistair knows because Alistair has my syllabus and has my lecture slides. So it will reference specifically, very specifically the lecture slides that are relevant for the midterm and what you should focus on, right? It tells you, look at lecture 1.2 for confounding and causality. Even the lecture slide numbers, it knows too. If you try to use ChatGPT for your homework, it'll do it, right? Another cat GIF missing. Okay. ChatGPT is a pushover, and it'll just give you the response. Whereas my Alistair tries to act more like a real TA, like a human TA, and tries to encourage growth and stepwise solutions. And that's really all for me. And I would like to thank everybody who worked with me on this, in particular Isaiah. Hi, Isaiah. So if you have any questions about this, you can find Isaiah afterwards or me. And next we'll hear from Suzanne.
Hi, everyone. Thank you for Thank you for joining us for this discussion. So I wanted to tell you a little bit about something that has been on a lot of people's minds, I think. Hopefully it's like faded into the background at this point, and hopefully it will not make its importance known again this year, and we'll have a quiet season. But I wanted to tell you a little bit about the air quality impacts that resulted from the fires that, the devastating fires that happened last January. And this work was, interestingly, kind of indirectly the result. It wouldn't have happened without federal funding, for sure, in so many ways, even though the direct funding for this particular project came from a tiny little bit of research funding that UCLA makes available internally. It's a really, really small amount of money. And ultimately, it comes from overhead, I believe, from federal grants. And UCLA felt like the fires were so important to the local community that it would direct a little bit of funding towards that. And also, most of this work was done by these two amazing graduate students. They wouldn't have been here without federal funding and being able to form this strike team to look at this really important issue. So what we set out to do in this sort of small project is to answer the questions: what was in the smoke? Was the smoke when urban areas were burning different from the smoke when it was mostly wildland areas? Did the fires impact air quality after the fires? And are the fires still impacting air quality? This is not a concern to everyone, but there are some people who are extremely concerned about this. I know of people who've left the state because they're so concerned about this. And so we had a look to see really whether or not that's a reasonable fear or not. To orient us, here's a satellite image of Southern California when the fires were burning. You can see smoke going in various directions. That's the Eaton fire. That's the Palisades fire. There's UCLA. We have some measurements from there, but and they're pretty interesting, but they take much longer to explain, so I don't have time for that. And then there's another star here, and this is a station where some recent UCLA graduates and also other scientists put up this really great instrument that's brand new. It cost the South Coast Air Quality Management District about $300,000, and it measures metals, a whole bunch of metals every hour. So we get this amazing hourly data. It's in that neighborhood because there's a lot of industrial pollution that the community is rightfully concerned about. But as it turned out during the fires, it was often directly downwind of the Eaton fire. It also was sometimes impacted by the sort of recirculating Palisades fire smoke. And then on the right, there's a diagram with kind of a lot going on. The yellow and green are basically the area of fire that's burning. So you can see that there's more area burning, and eventually, we got control of the fires. The blue bars show what percent of the area that was burning at any given time was an urban area. So mostly the urban contribution was up to 50% in the first couple of days. And then after that, it was a much lower fraction of the total area that was being burned. So this shows some hourly data during the fire. I'm sorry, I forgot to put the scale, but this is January 6th, and that's January 7th. That red line is when the fire started. And what we see at that station is shortly after the fire start, we have enormous concentrations of what are referred to as PM 2.5. PM 2.5 is something that we're really concerned about. It's tiny little particles that can penetrate all the way into your deep lungs. Your body has very limited ability to remove those particles. So our annual average concentration of those on this scale is around 10 micrograms per cubic meter. Concentrations went up to 300 micrograms per cubic meter in that smoke plume. Obviously not good. And then the lower panel shows the concentrations of lead. So normally lead is quite low. Sometimes it's below the detection limit, and it went up. So the fine particles went up by a factor of around 20 compared to the usual levels. The lead went up by a factor of 250. So those particles contain way more lead than normal urban particles. And then we see that the smoke plume basically hit our site 4 times. The first 2 were when there was a lot of urban burning, and the second 2 were when there was a lot of burning of natural areas. And interestingly, the thing that sticks out, you can immediately see, is that there's just as much lead when those natural areas are burning, which we were quite surprised at. And honestly, I don't really know what the explanation is, because we sort of assumed that the lead was coming mostly from things like lead paint in the buildings that were being burned. So as scientists, we can't just say, oh, the smoke plume came here. We gotta actually prove it. So I thought I would show you a little bit about this wonderful model that the National Oceanographic and Atmospheric Administration has been running for years. It's this incredible tool. Anybody can use it for free. It's pretty easy to use, actually, and it can calculate where the air was in the hours prior to arriving at a particular site for anywhere on the globe for any year back to 1948. And so far, the site is still up with the government shutdown. I don't know. Hopefully it'll stay up, but it's a really great tool. And you can see that is the Eaton fire, and that's our site where we're making our measurements. A lot of times it's in direct line of fire. Sometimes there's more air swirling around. So another way to look at the data, we have a whole bunch of more fancy statistical analyses, but another way to look at the data and look at the question of what is happening afterwards is shown here. So this is the fine particles, and we see that the fine particles pretty much go back to where they were before. Actually, they look a little bit lower. That's what we'd expect, because after the fires is the spring and the rains finally came, and the concentrations do go down a little bit when it rains. And then we see the lead. There are some occasional very high spikes, but in general, it's, if anything, lower than it was before. And also the arsenic, which is another thing that was highly elevated. That's lovely to think about too, right? That was also highly elevated during the fires, and it's clearly back to normal. So we get back to our questions. What was in the smoke? There were very high concentrations of lead, arsenic, chlorine, copper, also polyaromatic hydrocarbons, which are the result of some of my colleagues' measurements, and also some complex organic material that makes some of the metals more toxic. So unfortunately, overall, the smoke particles are more toxic than garden variety urban air pollution particles, which also are not a good idea to breathe if you can possibly avoid it. So the next question is, was the smoke from the urban areas different from the wildland areas? Surprisingly, no. It's a kind of an interesting question, maybe needs more research. Did the fires impact the air quality after the fires? So yes, but only for about a week. So, and that's actually totally what we would expect. Those fine particles stay in the air for around a week. After that, there's really no credible evidence that there's this toxic layer of something or whatever it is that people imagine in the general city. In the burn areas, it's a different story. But compared to the urban background, we really can't see any difference before and after. So yeah, that's sort of that question. So definitely we should all try and avoid smoke exposure when fires are happening, and be concerned about it for a little while afterwards. But after that, we don't need to be overly concerned. And with that, I will say thank you very much, and maybe give it back to Miguel.
Thank you, Suzanne. So this concludes this particular session of EYU. Now we will continue with our regular program, and the normal scientific talks.